There we go. Okay. Green screen. Yeah, there you go. All right. Hello and welcome back after technical difficulties caused by Apple conspirators, obviously. We are back to solve this and other problems. So, looking at the problem, we have the tangent. This is tangent x.
We already did this one, I think.
No, we started. Because secant, yeah, I was, but all of the, yeah, everything was lost. So now I have to redo this. So we have infinity over infinity. So we are going to take derivatives. X goes pi over 2 minus, and get secant squared x divided by negative 6 over 2x minus pi squared, which further, using just algebra, we are going to write as 1 over cosine squared x divided by negative 6 over 2x minus pi squared. And if we do more algebra to take care of the double fraction, I will put 2x minus pi squared on top and negative 6 cosine squared x on the bottom in denominator. So now when we plug in pi over 2, what do we get? Exactly, we get 0 over 0, right? So now we get 0 over 0 because pi minus pi is 0 squared is 0, and cosine of pi over 2 is 0, so 0 over 0. We can use L'Hopital again, which is equal to the limit x goes to pi over 2 from the left, and when we take a derivative, we will going to get 2x minus pi times the 2 as a chain rule. So first 2 is the 2 that drops, and then the second 2 is the one from the chain rule. And in denominator we have negative 12 cosine x sine x. Now the trick is to see, well, first of all, we can cancel these 2's, but don't. Keep one of the 2's so that you can compress denominator into sine of a double angle. So we have negative. I'm going to steal a 2 on the bottom, so now it's going to be negative 6 sine 2x. And on top you have 4 2x minus pi. So when you put in pi over 2, this is still 0 over 0. So now we can cancel 4 and 6 actually now, get 2 and 3. So I still have limit x goes to pi minus, or pi over 2 minus, which means from the left. And then when I take derivative in the numerator, I have copy constant 2, and derivative of the inside is just 4. And on the bottom, I have negative 3 times 2 is negative 6 cosine 2x. And there we go. So now, when you plug in negative pi over 2, that becomes negative pi, which is positive 1, So you get 4 over negative 6, negative 1, which is 2/3, I believe. There we go. So it worked out to be 2/3. Now, again, you can always use Wolfram Alpha Mathematica to verify these results. So those are the base cases, when you have infinity over infinity and 0 divided by 0. Now we are going to take a look at the cases that can be converted into 0 over 0, infinity over infinity. So you have to do some algebra to convert them first, and then use L'Hopital rule. L'Hopital rule works only for infinity over infinity and 0 over 0, so for indeterminate forms. But we have cases 0 times infinity case. That's also possible. So to give you an example, say limit of x times cosecant of x as x goes to 0. So this is 0 times infinity case. Now the trick is to write the function as 1 divided by 1 over f. See, that's the same. If you divide 1 by the reciprocal of the function, you get the same function. So we're just going to use that trick, and we are going to get what we need. So over here, I'm going to immediately rewrite this problem as limit x goes to 0. Keep the cosecant x. Actually, no, it's better to switch cosecant x, right? So it's x divided by 1 over cosecant x. And what's 1 over cosecant x? Very good. So now you see that you have 0 over 0, and you can use L'Hopital to get the answer. So we are going to use this formula every time when you have 0 times infinity or infinity times 0, commutative, right? You will use this formula to turn it into either infinity over infinity or 0 over 0. Let's see another example that you might like. Okay. So let's see this one. It says limit x goes to 0 plus, meaning from the right, of the sine x times the square root of 1 minus x over x. Beautiful, right? How much is sine of 0? Excellent. So you have 0 times infinity. Good talk, good talk. Let's see. So this is what I'm going to do. I'm going to switch the sign into cosecant. Now this is algebraic step, which means we don't worry about writing LH. Now cosecant goes to infinity and the square root goes to infinity. So now is the time to write LH. Don't forget to copy the limit. And now we take derivatives. What's the derivative of cosecant? Very good. Negative. And how about the top? Top is even worse. I wonder if we change the other one. So the derivative on top, 1 minus x over x, that's a half, and that's the half. So minus x over x times 1/2 of negative 1 over 1 minus x minus 1/2 1 over x. That will be the derivative. I use the logarithmic differentiation. If x goes to 0 plus. Now let's see. If I factor out negative 1/2, negative that will cancel, so 2 cosecant x cotangent x. I have square root of 1 minus x over x, and over here in parentheses I have 1 over 1 minus x over plus 1 over x, because I took out negative 1/2. There's a lot of algebra here. Okay, so now I have to clear all this algebra, see what's left. So when I multiply the first two, the square root will remain in denominator, so I will have 1 over square root of x times 1 minus x. And then plus square root of 1 minus x over x, and then 1 over x in front, divided by 2 cosecant x. I don't like this one, this way. Yeah, I'm going to switch the other one, because we are not getting far with this. The denominator is still infinity. We did not achieve anything. So let's switch. So tried it, didn't work out. I'm just going to cross it out and try again. So we have sine x square root of 1 minus x over x. Okay. So this is going to be limit. X goes to 0 plus. I leave sine x on top. And the bottom will be now square root of x over 1 minus x. Now, did I achieve what I wanted? I have to check. This is a side note, because I know that this is 0 on top. But is this one 0? Right when I plug in 0. So I have to check that. So I have to take the limit of square root of x over 1 minus x as x goes to 0 plus, which is square root of, so that's 0 divided by 1 minus 0, which is square root of 0, which is 0. Awesome. So we do have 0 over 0, and now we can take derivatives there. So by L'Hopital, we have a limit x goes to 0 plus. The derivative of sine x is cosine x, and the derivative in denominator is going to be square root of x over 1 minus x, and then the logarithmic differentiation is 1 over x, or 1/2, because the square root, and then minus denominator, another 1/2, and that would be 1 minus x there. I'm thinking this is going to work out to be 0, but let's see. So now in denominator, that's the most troubling part. It's to 0 plus. All right, so on top we have cosine x. When you plug in 0, cosine of 0 is 1. So numerator is not an issue. Denominator might be. So do I distribute? I can pull half out. If I plug in 0, yeah, this term over here is a problem. That's a problem term. All right, so kick 1/2 out. We are left with square root of x over 1 minus x multiplied by 1 over x minus 1 over 1 minus x. If you take a look, every other term is fine except that one. 1 over x will give us infinity there. Right? If you get a 0 somewhere, well, you can still keep computing with 0. You can't compute with infinity. So that's the only term that I really don't like. Let's distribute everything, see what we get. 2 times, we have cosine x in the numerator. I have, so now this one distributes over both, right? When 1 over x goes under the square root, it becomes 1 over x squared. Then 1x cancels. So the first square root is the square root of 1 over x, 1 minus x. And then we have minus. And the second one is going to be x do I do square root again? Yeah, why not? So it's going to be x over 1 minus x cubed. It's just a little bit of algebra, right? Because I have one, if you're not following what happened here, how is this cubed, I have 2 square roots in this one and 1 square root here, so together 3. So I'm not worried about terms 1 minus x. It's this x over here that it's really a problem. Because again, that still gives us infinity. So if I am to multiply top and bottom by x now, to try to get rid of that, it's going to be x squared there, but that's okay. I get limit goes to 0 plus, in the numerator x cosine x, and in the denominator 2 square root of x over 1 minus x minus x cubed over 1 minus x. Cubed, also square root. Alright, that worked. That worked. I forgot these parentheses. There need to be brackets over here because 2 multiplies everything. Alright, so now when you plug in 0, the entire denominator is 0 and the top is 0, and we are back where we started. Did not achieve anything. This is really evil problem. I like it. This one is really bad. Because we still have 0 over 0, and the problem is much more complicated, which means that we made a wrong choice what to swap. But when I did the previous one, problem was still more complicated. It was getting more complicated, and we still haven't achieved a lot. It seems that the answer is 0. Trying to see if there is anything else that we can do differently. Then I check if I copy the problem right. And I did. This is problem 50 in your textbook. So you have something to look forward to, you know, at homework. Oh, yes. How do we do this? You finally. This problem took us almost 30 minutes now. With technical difficulties, we're at 30-minute mark on this problem. So can you just fix this real quick so we can move on? Okay, so it starts so nicely, and then it just goes crazy. New idea. I'm just going to say run. So again, same problem for the third time. This is my new idea. Limit x goes to 0 plus sine x square root of 1 minus x over x. Split the problem this way. limit x goes to 0 plus sine x square root of 1 minus x, everything divided by root x. Why not? We can break the square root using the algebra. And now, when you plug in 0, this one over here is 0, making everything 0 on top, and the bottom is 0. So we have 0 over 0 right away. Now take derivatives. So I use L'Hopital rule now. You're going to have product rule in the numerator. So copy the first, take derivative of the second, plus copy the second times derivative of the first, divided by 1 over 2 root x. Problem solved. Whew. There we go. Which would be a good time for us to actually stop and talk about importance of never giving up in life. But I have to solve after 40 minutes of doing the same problem. But let's first finish this. So when I multiply by 2 root x, then we have no more denominators. In that case, we have negative 2 root x sine x over 2 square root of 1 minus x plus 2 times square root of x 1 minus x cosine x. And now when you plug in 0, 0 will kill this term completely because root x goes to 0, sine x goes to 0, 1 minus x in the denominator goes to 1. So you have 0 divided by 1. So first term is awesome. Second term, this dies to 0. This is 1. This is 1. So 0 times 1 times 1, right? Still 0. We have 0 plus 0. And as I said, answer is 0. It's just that I couldn't get it. How many times did it take me?
Just one for me. I lost track after 3.
3 times. This is the third approach to the problem in a different way. So I want to discuss those 3 because you should always learn from your failures. And I don't know where I read that or heard that. Someone said, I mean, I don't pray, but they say pray for the failure because that's where you learn the most. Not every time, but this time, this was a very good learning experience, at least for me, if not for you. Oh, I need those.
Oh, yeah.
Thank you. Gonna teach them. So, I want to go back at the beginning of this problem. It looks so nice, right? You have 0 times infinity, and it's easier to switch sine x because you guys just go 1 over sine. 1 over sine is cosecant. There we go. And then just, follow with the derivative, which turned out to be insane. Now, why did I abandon it and cross it out? Because the expression that I got here was vastly more complicated than where we started, with still infinities around, right? Because cosecant of 0 is infinity. So I said, all right, I tried flipping this one, and it gave me something much worse. When you run and you hit the brick wall, you turn around and run the other way, right? So I said, all right, let's switch the second one then, which is the second try, which is this. So I'm switching the second one, which means flip it. There it is. And that didn't work. because you have to put 1 over this, but when you put 1 over this, it's the same as just swapping it. So that's why it's x over 1 minus x. And then I started taking derivatives and distributing and wondering, and still I get something that still has infinities, because this is 0 over 1 and 0 over 1. So that turns out to be 0. So I have 0 in denominator. Again, still not good. I mean, I have 0 here, 0 over 0. This is 0 over 0, but then take the derivative again, right? It makes it worse still. That means that the basic idea of flipping either one of those doesn't work very well. So then I went and I decided on a take 3 to take a composite function and break it into 2 functions. And here is the now top function, the bottom function, 0 over 0, from where it worked in 2 steps. So the moral of the story is what? Exactly, I'm the smartest guy alive. Exactly.
Last on the test.
No. So yeah, the moral of the story is just never give up. Never give up, and keep pounding. Things eventually work. Eventually work out. Do we want to do more? Of course we do. Because there is more. We've seen 0 over 0, infinity over infinity, which are the basic indeterminate forms. And then 0 times infinity, where we use f equals 1 over f. Now we are going to take a look at infinity minus infinity. And this is one of those that's like, really? You can subtract 2 infinities? And I say yes and get 3/4. That's awesome. So let's see infinity minus infinity case, or cases. Now, these guys can result in infinity, in 0, or any number. That depends on rate of growth of functions and which functions are being subtracted. So let's take a look at 2 examples, and then you guys can enjoy the rest. So I can do, let's say, 53, 54. You have 51, 52 to practice, and then you should have a whole bunch of those on your online homework as well. So let's start with 53, say. That's a nice one. You love trig, so it contains trig. Theta goes to pi over 2 from the left of tangent theta minus secant theta. So this is infinity minus infinity. Now remember what you need. You need infinity divided by infinity, or 0 divided by 0. How do you go from subtraction into division? And the answer is through factoring and multiplication, okay? So I'm going to give you a map for infinity minus infinity. And the map says factor, which gives you multiplication, then flip, then L'Hopital. Now this makes no sense right now until you see what I mean by this. But I write tangent as sine over cosine, and secant as 1 over cosine theta. And now here is the first one, which is factor. I am going to factor 1 over cosine because that changes the main operation from subtraction into multiplication. And then I should be at that 0 times infinity case. And then flip one, and you should be ready for L'Hopital. So now I'm factoring 1 over cosine theta times sine theta minus 1. And if you look at this, cosine of pi over 2 is 0, so that one is infinity. Sine of pi over 2 is 1. 1 minus 1 is 0, so you have 0 times infinity, and you can now use the trick, which is to flip. So limit theta goes to pi over 2 from the left, and now you decide which one to flip, which hopefully is this cosine. So you leave sine theta minus 1 on top, and then 1 over cosine goes down as the cosine theta. Now when you plug in pi over 2, you get 0 over 0, which is good for L'Hopital. Derivative of sine is cosine, so I have a cosine theta on top and negative sine theta on the bottom, which is 0. So we subtracted these functions, theta minus secant, tangent minus secant, and we have answer of 0. So this was one of the infinity minus infinity problems. Now, one more time. You are starting with subtraction. The way to get to division is through multiplication, which is obtained by factoring. So you should constantly think about which portions, which terms you get to factor to make that multiplication. Let's take a look at 54. It's the same situation. We have limit x goes to infinity, and then I have x minus square root of x squared plus 4x. So what's the process over here? Well, we clearly see infinity minus infinity, because when you plug in infinity into x squared and x over there, you get infinity plus infinity, root of infinity is infinity. So you definitely have infinity minus infinity. Now, the question is, how do we solve the problem? You know that you have to change this subtraction. So this subtraction here is your major, main operation, right? In order to get rid of that one, you have to be able to factor out x, which means that you need x in front of the square root. Now, where do you get x from the square root? Well, you hopefully can have x squared under the square root to factor it out. But then you have two terms under the square root, which means now you have to figure out how to factor x squared first, and then that escapes as x, and then you factor out x. A little bit convoluted, but it works. So let's see. The first step for me is to factor out x squared somehow under the radical. Well, that's easy, because if I factor out x squared from the first one, I'm left with 1 plus 4 over x. If I take x squared out of 4x, 4 over x stays behind. Now, if you don't believe that, just multiply back. X squared times 1 is x squared, and x squared times this, x and x will cancel, you get 4x, right? So that's a little algebra trick that you need. Now, x squared is going to go outside as x. So I have x minus x, square root of 1 plus 4 over x. And finally, you see that I have x minus x there. Both terms have x. You can kick that out. So that becomes, you kick x out, and you're left with 1 minus the square root of 1 plus 4 over x. All right, so now is the time to check because you have multiplication. Finally, you have multiplication. This better be 0 times infinity, otherwise, right? So x is going to give you infinity, and the other one is going to give you 0. Because when you plug infinity here, 4 over infinity is 0, 1 plus 0 is 1, root of 1 is 1, 1 minus 1 is 0. So we do have infinity times 0. That means that we can use our trick f equals 1 over f. So this is equivalent to leave the complicated one as is and change the other one, which is x goes downstairs as 1 over x. Do you see 0 over 0? Hopefully you see 0 over 0, because when you plug in infinity, you get 0 over 0. We can finally start doing the problem. We're done with algebra. So now the derivative, well, the one on the bottom I told you, just memorize it, right? It's the numerator one that we have to worry about. And what is that numerator? So I like to write it on the side so that I can take the derivative easily. First of all, I know that the derivative of 1 is 0, so I don't have to bother with that. The only thing that I bother with is negative 1 minus 4x to the minus 1 to the 1/2. So I put this x up and put the exponent of negative 1 on it. The square root of the entire thing is 1/2. I copy this minus in front. Don't worry about 1 because the derivative of 1 is 0. So I need to take the derivative of this, which should be easy, right? Because 1/2 jumps in front, you pick up negative 1/2 there, and times the derivative of the inside, which has that x. So now what do I have? The derivative would be negative 1/2 times 1 minus 4x to the minus 1 to the negative 1/2, because you subtracted 1, times the derivative of the inside. The derivative of the inside is you copy negative 4, right? Derivative of 1 is 0. Copy negative 4, and then the derivative of this x is negative 1x to the negative 2. So now we can clear some stuff up, simplify it. So these negatives drop. I have 1 over x squared in the denominator, and in the numerator I have 2 square roots of 1 minus 4 over x, and on top I have 4 over x squared. Now I hope that you see that when you multiply x squared and x squared, you immediately lose the double fraction. Oh, I did not put L'Hopital over here. There we go. So I still have limit x goes to infinity, and x squared and x squared. So now that becomes 4 over 2 square root of 1 minus 4 over x, and that's it. So this time around, infinity minus infinity equals to 2. It depends on what functions you have. Now, not every infinity is the same. There are different types of infinities. And they would subtract to different values. So if you subtract infinities of the same order, they subtract to 0. But when you subtract infinities of different order, they might subtract to 0 or a number or infinity. So infinity minus infinity can still be infinity, depending on what order infinities you're subtracting. And that's solely given by these functions, which actually represent different types of numbers. Yes?
So these represent like growth rates, right? When you're comparing to
Beautiful. Yes.
Like,
Yes.
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 Please explain in better words than I can do.
All right, so Brian already seen. He's been here only 5 minutes and he already knows. But he's drinking some triple espresso coffee or something. Growth rate of functions. Growth rate of functions does play a role, even though it's not easy to determine that just by looking at it. But you know that ln x is a sluggish growing, and then you have a square root, and then you have polynomials, and then you have exponentials, right? So when you're dealing with subtracting those, depends which one is first, which one is second, which one grows faster, and by how much or how fast. So all of those factors contribute together to come up with these answers. So as I said, your answer could be, 2/3, your answer could be 2, your answer could be 0, your answer could be infinity. So you can't just go and say, oh, infinity minus infinity is 0 because 3 minus 3 is 0. It doesn't work the same way because 3 is just 3. 1, 2, 3, done. Where infinity has different orders and levels to it. So it's not as trivial. We have one more type of problems. There's actually 3 different types of problems, which is all the same family. They're solved the same way. And the lecture is over. Right? Of course. That's why you have to wait. See? You're done, so bless you now. You've been cut off.
Nah, dude. I don't want you to get spoiled. Just like next time.
Exactly.
Yeah. So can't even dog you. You should get tissue, dude.
I have this one. Bleach.
Oh, good.
Do I?
I need these lace tissues. Maybe I'll get better.
Yeah, I know.
Little way.
Okay, there they are. The wonderful, one and only group of problems that look like this. They're all exponential type. So 1 to infinity. And you would say, well, that better be 1. Well, it's not. And then 0 to 0. 0 raised to any exponent is 0, and any exponent raised to 0 is 1. But 1 is not the same as 0, so which one wins? Depends on the function. And then you also have infinity raised to 0. Is the answer 0? Is the answer 1? Or anything in between, right? So all of these problems are solved the same way. And here is the trick. Set problem equal, I'll write it, to y, then ln both sides. Easy. So let's take a look at introductory examples. Say limit x goes to 0, x raised to x. Now this is 0 raised to the 0 case. So the procedure says that you are supposed to set this problem equal to y and then ln both sides. Now you can put ln directly inside the limit. So now you have that ln y is equal to the limit x goes to 0 of x ln x, because you know the rule for limits, which says that the ln x to the p is p ln x. So this x, this p, which is x in this case, went in front of the limit. So this is how this x ended up there. Once we achieve that, we check and we have 0 times infinity. 0 times negative infinity, but it's the same thing. So ln y is equal to the limit x goes to 0 of ln x divided by 1 over x. And if you carefully observe now, you have infinity over infinity, which is good for L'Hopital rule. Limit x goes to 0, and you get derivative of ln x is 1 over x, and the one on the bottom is 1 over x squared. So all of this works out to be negative x, which is 0 at the end. So what you got is that ln y is equal to 0, but remember that y was x to the x. So if you e both sides, you get y equal e to the 0, which is 1. So what's the limit? Limit of x to the x is 1. Remember that. Now there is some confusion, so I'll just say this just in case. If you already understand this and seen it, don't be offended, because I have to say it. It's my job, all right? What I got here is that y is equal to 1. And then I wrote this. And probably someone is going, what the hell? But not saying anything. Observe over here that if you ignore the red, that I define that y is equal to the limit of x to x. So y is equal with the limit being there. That means that y is equal to whatever we get once the limit is already solved. So that's why I'm replacing y with the entire limit x to the x. One more example, and we're done with this section. All of these examples are done the same way. So limit x goes to infinity, 1 plus 3 over x raised to the x. Same procedure. Leave a little bit of space to squeeze ln in. put two ln's, then put the x down, and solve it. No pressure, I'll give you 2 minutes. No coughing.
Yeah, good luck enforcing that one.
So that's the solution. We see it's infinity times 0, change it into 0 over 0, take derivatives. It is, as I said earlier, convenient to memorize that the derivative of 1 over x is negative 1 over x squared, which makes that 3 over x negative 3 over x squared, right? It's quick to take those derivatives if you memorize that the derivative of 1 over x is negative 1 over x squared. And that takes care of the stuff. So I'm going to take a break and then finish chapter 4.